Hello, this is Ed. I'm the CTO and the co-founder of PingCap. PingCap is a database company, and we built TiDB, and which is Go-based distributed database. So today I want to share something besides TiDB, and I want to talk about something about Go. So the title is The Dark Side of Go. So yeah, if you are a Pink Floyd fan, you might be know what I'm talking about, right? So I just want to say for someone who haven't heard about TiDB before, and all you need to know is that TiDB is a distributed SQL database with MySQL compatible syntax and the wire protocol. And it's really popular. But today, all you need to know is this. It is not the sales pitching slides. Today we are going to talk about and focusing on the Go part. Okay. Well, this is today's agenda. I will share some really weird on-call issue. Some really weird situations happens in our users in production scenario. For example, like some weird the latency jitter under the high load due to the Go's fair scheduling policy, or some weird memory control, something like an abnormal memory usage due to the THP, the Linux THP, the transparent huge pages, and some about some weird cases about the GC garbage collection. It is a very common topics when we are talking about the Go runtime. And we'll mention about something about the NUMA architecture. Yeah, so let's go. Part one, the scheduler, about the scheduler. Let's imagine a very common situation, just like this. For example, it is a very typical MPSC pattern. You have multiple go routine and send the request to the channel, and you have another go routine to, it's a loop, read from the channel and do the jobs. And this channel always used to batch the request, and this go routine always read from the channel. And this pattern, I want to say, is so common. So I think every network application which is written in Go use this pattern. But we found some very weird situation. Once something like we take a look at some of our users, they have some weird latency jitter when the system load, the machine load, and the CPU usage is high. But the network IO pressure is reasonable. But why there's some high peak of the network latency? So this is the case. As you can see, the network is ready here. And then the go routine for this IO request woke up at about 4.3 milliseconds after. So that means the system have already this go routine are switched to the background, and even though the network is ready, but your network packet cannot send within this 3.4 milliseconds. And sometimes we even notice some more than 10 milliseconds latency here. So that means the time spent on the runtime scheduling is not negligible. But this situation only happens when your CPU is overloaded. But the root cause of this kind of issue is that the fair scheduling policy, because Go's runtime treat every goroutine as the same, right? So no one is special. But in this pattern, this goroutine is very special because you have to wait this goroutine to handle the request and then return back to the goroutine. So this one is special, but the runtime may do the context switching, and this goroutine will be may not be get enough CPU time. So that's the root cause of this kind of situations. So in this case, we don't have a very good. In this case, we can see we don't. But this pattern is so common, right? But we don't have the very good solution for this kind of situation. When the CPU load is really high, the performance of this pattern will not be very good. So I think one, don't make your CPU too busy, right? And I think another solution for this is offload the CPU intensive module to other process, and change the priority of the process on operating system. Yeah. The second part is memory control, and the memory control is a big topic, and let's take a back. Let's talk about some background information about when we are talking about the memory. So in the Go world, I think we divided the memory into this many kind of types, and in this three, the first, second, and the third one, we should pay more attention. One is the memory really allocated from the OS. Go's runtime use mmap to map the memory, to allocate memory from the OS. And the second one is actually Go's runtime is Go have a GC module, and so that means Go's runtime it manage the memory by itself. So even though you in your GC in your application retain the memory to system, it is not used anymore. But that means the memory is still held by the Go's runtime, but it is not returned to the OS immediately. So that means sometimes you see, hey, I'm not using this memory anymore, but it is not returned to the system. It's still held by the Go runtime. And the third one is the memory we actually in use. That is it is very easy to understand. Okay. So this is a dashboard. It is a dashboard. It is metric of memory usage in TiDB's Grafana dashboard. So as we can see, the yellow part is the actual memory we are using, and the red part, the red line with the dots is the GC threshold. So the GC threshold is always the 2 times. It is configurable 2 times compares to the memory actually in use. So the things we should pay more attention is the reserved by Go. It is the managed memory pool by Go. So it is the orange part, as you can see, and the green line behind the green line is the actual memory allocated from the OS. As you can see here, sometimes the memory reserved by Go may be more than the memory actually allocated from the OS. It is normal. It is totally normal because the Go runtime use mmap to allocate memory. So it is actually quite normal situation for using syscall mmap. Okay. Another background is PHP. The transparent huge page. It is a new features introduced in some newer version of Linux kernel. And before we're talking about the PHP, I want to share some background information about the TLB. It is it's like a cache. It is like a cache. When operating system want to map the virtual address to the physical memory, if you look at the TLB in the CPU, and if the page entry cache doesn't hit, you have to go to the memory lookup, which is slower, right? So TLB is a hardware, so there is a limit that how many entries, how many page records it can cache, right? So by default, the operating system use 4K page size. So that means that if you have a very huge memory, very large memory, that means you may have a lot of page entry records in page records. So that means the percentage of the entries that can be cached in TLB is limited, right? The number is not too much. The percentage of because there are so many page entries. If you are using 4K, the page size. So the idea behind the THP is that if we increase the memory page size to 2 megabytes or more, that means the lower the entries of the page entry records, the records go down. That means the percentage of the cache hit will go up, right? So that means the random memory accesses can have a better performance. So this is the idea behind the THP, and the users and the developers will not. You should not care about this thing. It is automatically managed by the operating system. So you don't need to worry about the details of THP, but sometimes it will be a very that may cause some very weird situations. Let us see. So this is an on-call issue of one of our customers' on-call report in their production environment that is related to the THP. And as we can see, the title of this report is TiDB memory usage is abnormal and the heap memory usage is incorrect. Let's see, this is the screenshot from the dashboard. As you can see, this process used near 200 gigabytes of memory, but others is quite normal. And it is very, unusual. And the system's available memory of this machine is not too much, so it's very dangerous situation. And we reproduce that situation. We write a little program running on this machine, and we take a look at the dashboard. In this diagram, we can see that the orange part, which is the Go, the memory managed by Go, reserved by Go runtime. The Go runtime things it is quite normal, right? It is it is normal, but and the Go runtime think it is not using that much memory, as we can see. However, at the operating system level, the operating system, the memory allocated from the operating system is allocate a lot of memory, and it is not decreased. So that's the problem, right? It is very weird. So let's take a look at the distribution of the memory, which kind of memory it used, and we check the prog, the S map to see the memory mapping for this process, and we see the very abnormal entry is the huge page. So you can see that this THP have a lot of memory allocation. This memory is occupied by this one. And if we compare this to other nodes with the THP option disabled, and we can see the memory allocation is quite normal, right? It is normal. It is not like this, right? It is just like the memory which is managed by Go's runtime, and we can see that the huge pages is 0 KB. Okay, so we think this is the root cause must be the root cause must be related to the THP, but why, right? And we check the source code of Go's runtime, and we think that Go's memory management is still in at the AKB page granularity, and the Go's runtime use API called madvice function to notice the operating system about to use the certain size of memory. But when THP enable, the adjust does a roundup operation to aligning upwards according to the size of the THP page size. So that means Go's runtime still thinks itself to be reasonably managing the memory using AKB memory pages. However, at the system operating system level, there are a lot of holes in the huge page, right, in the memory space, because of the page is so big that can easily create a lot of holes, fragments, right? That this kind of fragments that will make the memory very difficult to be reclaimed by the OS. So from the situation, we can see we still hold a lot of memories. And another more confusing behavior by the OS is that there is a procedure, there's a behavior behind the THP. When for example, when your user program return for example, you allocate the 4K memory from the OS, and you return back to the OS, and that sometimes that may cause more amplification when you return the memory to the OS. because when we return back to something like the 4K pages to the OS, and there's a background program that called K huge page D. This program will turn will merge the 4K pages from the user applications and merge them into 2 megabytes and return back to the OS. So that means on the merging process, that may bloating the process ISS by as much as 512 times larger than your 4K. For example, because this program may allocate the 2 megabytes buffer just for the 4K page to merge them into one page, right? It is we see some clues from the Ghost source code here. Okay. So the follow-up is really simple. We just tell the users to check if you open the THP, you have to turn it off. Just like MySQL, Oracle, and a lot of database did, because sometimes we have to, the runtime, the system, that they may want to manage the memory by their own, just like TiDB did, not just using the usage pattern of THP is not like the usage pattern of database. Okay. Another part is some GC related scenarios. As you know, Go use mark and sweep GC model, and especially I think since 1.8 version, the stopped the vote STW time for the GC have been greatly reduced. So many people are saying, hey, there's not a big problem of STW. And the Ghost GC performance so well, and we don't need to care about it anymore. But the reality is that, however, if you, I would like you to consider a very extreme scenarios, like what if your memory allocation speed is much faster than the GC speed, right? Do you think this problem before? Imagine that if you don't have a STW time, how to make GC module to reclaim the memory to do the garbage collecting. So the answer is that the GC of Go will run the cleanup process every time. If you happen to have the situation that you have the very fast memory allocation, the speed of memory allocation faster than the GC, and the GC model will block the allocation process. For example, when you want to allocate the memory from the in your code, and before the system give you the memory you want, you will run the GC process, cleanup process before. So that means that will slow down the memory allocation. This is known as the mark assist. When you use pprof to look up your core stack, you can see some mark assist here. That means your memory allocation is helping the GC model. And the Ghost runtime will allocate a quarter of CPU, 25% of CPU to dedicate to the GC model when you are when you want to run the cleanup process on your memory allocation process. So this is a real world case study. We noticed some weird latency, even for some simple request to our database. And the weird latency is from 30 milliseconds to 800 milliseconds, even for a simple random lookup. And we are sure that the CPU and the network load is quite normal. So that means the query, a TiDB is a database. The performance is really important. The stability of the performance is really important to us. So this is unacceptable, right? If you are just running the simple query and the latency jump up and down from 30 milliseconds to near 1 second, and there's no problem with the I/O, CPU, and network. You are sure about that. But so we are we are very curious about where does the latency come from, right? So just like other Gopher do, we use pperf to do the investigation. And we get the trace information from pperf, and we can see that the query is blocked by the GC sweep. Yeah, right. That you can see the sweep here, and we take a look at the core stack, and we found some very weird scenarios. Like as you can see, this is our application code here. We just called a very normal new function to allocate the memory from the OS, and then the core stack jumped to the GC part, right? The GC part, and that this simple function call takes about near 317 milliseconds, right? It is very unusual. So from this from this case, we can see that the GC models, even though the STW, the start vote, is acceptable, but the GC model can block the program, can block your application just more than the STW. It is possible to block any individual goroutine when you want to allocate memory. So even without STW, it will be block your application. So, but this situation is very weird. But why so long, right? Let's take a look at the sweep process in the GC in this case. The sweep function, this process have already scanned 1 GB of memory. That's why it takes so long, right? The scanning 1 GB of memory, but just for releasing 8 KB, reclaimed 8 KB of memory. So that's weird. There must be some bugs hidden inside this scenario. So we found similar issues in Go's GitHub issues, and we're really glad to see that the Go team have already fixed this one. The fix is also very simple. The fix is very simple. This code says that the sweep assist cause this high latency, even if there is no garbage. It have been scanning the memory blocks for a long time and haven't found a single free slot. And this process, the old process, is just keep logging, never stop. The fix is also very simple. They just set upper limit on the scanning process when scanning process scanning limit, just not scanning all the memory object all the time, right? And we just use a newer version of Go with this patch, and the problem is fixed, and the latency jitter is gone. So that means that is the right fix. But we are also very curious that how TiDB triggered this bug, right? We found that there is a very unusual, abnormal usage in our code. We use pperf to take a look at our memory usage. We found that there is a module called statistic. This module uses a lot of AKB small object. As you can see, it uses about 4 gigabytes of the memory. Or all of this is long-lived AKB objects. And all these objects are all alive. It is a long-lived object. So that means they are all alive after GC. So in the old version of Go's runtime, in this situation, the GC process will do the sweep and look up the linked list of the memory objects, and until it found the free slot to free, and then it stopped. But in our situation, that means there's a lot of small object here. So and that means we in the old version of Go's runtime that will scan all the time until this. So yeah, that caused the latency. So in this case, we know that although the STW duration is low enough for Go, but still we can have some unexpected latency jitter just because the GC still exists. You will need some when you have when your allocation speed is faster than the GC speed. That may cause some unexpected block for your application, even for some individual goroutine. Another situation, very weird situation caused by the related to the runtime and the GC module is when you have so many cores of on your machine, and you may notice that some situation that if you have single server, single process, multi-thread versus multi-process plus and you binding the CPU cores to specific process. Let me say, let's say that single process, multi-thread versus multi-process and bind the CPU to the specific process. And sometimes the multi-process part can get a better performance, higher performance. And I will share something about this phenomenon. Okay, and we can take a look at this on-call issue. It is we met a QPS bottleneck, but we checked the CPU usage is about 16%, and just like does it like familiar, right? The CPU is around 60%, is not well used, and the network and I/O both okay, not under very high pressure, and we continue increase the client the concurrency, but the system throughput doesn't increase. by the number of concurrency increased. So it seems the results are not exhausted, but where is the bottleneck in this case? I think we can have some hypothesis that there must be some reason why the CPU is not being used, right? Sometimes, and the very common guess is the CPU must be waiting something or asleep somewhere, right? Let's make some assumptions, and there may be some logs, some mutex, and maybe the GC module, just like the previous case, and that, or some NUMA deployment related problems, and we can verify them one by one. Okay. So is it caused by some useless, unuseful mutex, right? Unnecessary mutex. Sometimes you take your application use a lot of logs, but it's not necessary. But when you have a very heavy log conflict, the CPU, the situation, the result of this situation is like the CPU is not well used, but your system is meets the bottleneck. So we just use some also use pprof mutex to find that to check out the mutex usage for in our application, and we found that some useless mutex in some of our module, and we fixed them. After this optimization, the QPS go up and the CPU usage go up. So that means our assumption of this is correct, but still not enough, right? That only proves that if we optimize the CPU usage for our application, the performance will go up. And is it caused by the NUMA? I will talk about something about NUMA in the next few slides. In this case, we changed the deployment module to separate the process, separate the deployment into different process. For example, because this machine have a lot of CPU cores, so we separate the TiDB process into many separated process and bind it to and dedicate the CPU cores to specific process, and that works well. That works really good. The QPS is much higher. You can see is jumped from the 5K to 7K, and the latency P 99.9 latency go down to 2 seconds, and the CPU usage significantly improved from 64 to near 90%. And I think the another interesting metrics is the page fault. Page fault is significantly decreased. So it's a very little change of the deployment method, but have the biggest improvement, right? So here is this is the experiment we did. The raw is the raw program. We don't have any optimizations in this case. So as you can see, there's a lot of the performance is not very good, and the CPU usage is not very high, and then we have a version that optimizes the mutex usage, and the CPU goes up, but the performance goes up, but not enough. And then we bind the CPU, separate process, and we can see the CPU finally we can use the CPU. And the page migration here, is 10 times lower compares to other deployment method. So, and another guess is GC, and we use the tool called the Linux KI to analyze the off CPU situation, and found that the 16/7 of the time is spent on sleeping. That's a signal that we have log the CPU is waiting for something, because only waiting for something that the CPU is sleeping, right? So we continue analyze the cause of the sleeping. We found that the function like mheap free span, which contributes about 40% of of total sleeping, right? And there are also other two that they are all indirectly from the GC module, and so our guess is also correct. It is the CPU usage is caused by some the low CPU usage is caused by indirectly caused by the GC module. So that is for the memory allocation module, there is a huge lock on Ghost runtime. To be exact, it is M central module, and then it comes. For example, when it comes very high frequency, high concurrent memory allocation, there will be a series lock conflict in this module. So that means the more CPU core you have, the bigger problem that becomes. That's why the performance of deploying the single process is lower than the single node multi-process model deployment, because of separate deployments, the conflicts of maybe relatively lower when each process have fewer CPU cores. But the Go team have already done a lot of work on it, but it's still on the way. So back to the NUMA part, back to the beginning, we can see that when you separated the process and set the CPU affinity, the performance is greatly improved. The reason behind this situation is it is about NUMA architecture. The point of NUMA is the NUMA architecture is, the idea is really simple. It just dedicate the memory direct to specific CPU core. So this core can directly access the memory of the memory it owns. That will not go to the NOS bridge. So it is memory affinity, the CPU memory affinity, just like look up the local memory, something like that. But that means when the CPU wants to read the remote memory not owned by itself, that means that will goes to the page migration process. There will be the higher latency. So this also caused the minor page faults for in this architecture. But very unfortunately, the Ghost runtime doesn't deal with the NUMA related stuff, and the Ghost GC is not NUMA aware. For example, when the goroutine does the context switching, or the GC runs the scanning, it is not NUMA aware. That means when you scanning the memory, when you use the memory not owned by this core, owned by the local NUMA core, that will trigger the OS memory page migration, as you can see here. For example, this is a GC module and is scanning the objects, but that causes a lot of the page faults. So yeah, it is that means that may affect the performance. Okay. So these factors makes Ghost runtime less scalable on the when you have a machine with large number of CPU cores. So this is the problem. We don't have a very elegant solution. So the only solutions for us for now is separate the deployment and binding the cores to the process. Yeah, this the solution. Okay, this is what all I want to share about some cases caused by the Ghost runtime in our in production scenarios. So this is a quick recap. The case one is the latency in batching the client request. The root cause is the fair scheduling policy. The case two is turn off your THP because Go handle manage the memory by itself, not the OS, not like the OS. The case three is the GC sweep may cause some, may block your individual Go routine because of there's some called the mark assist mechanism. And the case four is the well-use of the mutex and the logs and NUMA, a better understanding of NUMA architecture may help you get a better performance. Just binding the cores, separated the process. It is about the scalability of on the machine with multiple cores. Okay, this is what I want to share, and this is my Twitter. You can follow me if you have any following questions. You can reach out me on Twitter, and this is our website. And if you interested in TiDB and it's all open source, you can check it out. Thank you.